Welcome to this video on distributions of the sample mean. After watching this video, you will be able to explain the phenomenon of sampling variability, define a sampling distribution, define the standard error of the mean, and calculate the mean and standard deviation of a sampling distribution given the population mean, population standard deviation, and sample size. Please watch my video entitled The Central Limit Theorem before watching this video. What is sampling variability? At the very beginning of this course, we learned that random samples are used to represent the population as a whole. So if this larger circle represents the population, we take a sample, which is randomly chosen, that is representative of the larger population. Sampling is done because surveying every member of the population is usually prohibitively expensive and time-consuming. Would you expect two different samples to contain the exact same data points? Pause this video, think about this question, write down your answer, and then unpause it. Suppose you roll a die 50 times and find the average of the 50 die rolls. Your friend does the exact same experiment at the exact same time with a different die. Would you expect your results and your friend's results to be exactly the same? You would not. Because the die roll is a random event, the resultant average is a random variable. Variation among samples is known as sampling variability. What is a sampling distribution? To account for sampling variability, we create a probability distribution with a sample mean and sample standard deviation called a sampling distribution. According to Sullivan, the sampling distribution of the sample mean, x bar, is the probability distribution of all possible values of the random variable x bar from a sample size n taken from a population with mean mu and standard deviation sigma. How to create a sampling distribution. In the past, we have used individual values, in other words, n equals 1, a sample size of 1, and plotted the random variable x onto a graph to generate the probability distribution of a population with population mean mu and standard deviation sigma. Notice that this graph will be populated with individual data points that were taken from the population. We're not going to do this anymore. Instead, what we're going to do is taking a sampling distribution. So instead of taking individual data points, we're going to take samples of size n, and n can be any number as long as it's larger than 1. Then we find the sample mean by averaging our data points, and we continue this until all distinct simple random samples of size n have been obtained. So we create this new graph, which is populated not with individual data points x, but with x bar, all these different sample means. So sampling distributions plot all possible values of the sample mean x bar with sample size n, which is, again, has to be larger than 1. This allows us to generate a probability distribution, which is used to estimate the population mean and population standard deviation. The mean and standard deviation of the sampling distribution of x bar. A simple random sample of size n is drawn from a population of mean mu and standard deviation sigma. The sampling distribution has a mean of mu sub x bar and a standard deviation sigma sub x bar, which is the population standard deviation divided by the square root of n. Remember, n is our sample size. The standard deviation of the sampling distribution is called the standard error of the mean. This equation tells us that as the sample size increases, the standard error of the mean, or the sampling distribution's standard deviation, will decrease. This makes sense on an intuitive level, as we expect variation among samples to decrease as our sample size increases. Population distribution versus sampling distribution, the central limit theorem. If a random variable x is normally distributed, the sampling distribution of the sample mean will be normally distributed. So in this case, again, if our population is normally distributed, then we don't have any restrictions on our sample size because we know if we're pulling from a normal distribution, we are going to generate a sampling distribution that is normally distributed. But what if our population is not normally distributed? What if it looks like one of these population distributions, or it looks like something else? It doesn't have to look like one of these four things. Then what? Well, the central limit theorem tells us that regardless of the shape of our original population distribution, if we take samples that are greater than or equal to 30, then our sampling distribution will be normally distributed, again, regardless of the shape of our population distribution. Again, these concepts of the central limit theorem are explained more thoroughly in my video entitled Central Limit Theorem. So if you have not already watched that and want a more thorough understanding of the central limit theorem, please watch that video. Example 1. A simple random sample of size n equals 50 is obtained from a population with a mean of 120 and a standard deviation of 13. Does the population need to be normally distributed in order for the sampling distribution of x bar to be approximately normally distributed? The key here is our sample size. Since our sample size is larger than 30, it doesn't matter what the shape of our population is because our sampling distribution is approximately normal for sample sizes larger than or equal to 30. So the underlying population does not need to be normally distributed because the central limit theorem states that for sample sizes greater than or equal to 30, the sampling distribution will be normally distributed regardless of the shape of the underlying population. Describe the shape of the sampling distribution of x bar. The sampling distribution of x bar will be approximately normally distributed. Again, we know this because our sample size is larger than 30. Now we want to use the same piece of information to find the mean and standard deviation of the sampling distribution. We're going to round all answers to 3 decimal places as needed. The mean of the sampling distribution is the same as the mean of the population. Therefore, the mean of the sampling distribution is 120. The standard deviation of the sampling distribution, also called the standard error of the mean, is the population standard deviation divided by the square root of n, where n is our sample size. Notice that our population standard deviation is 13, our sample size is 50. So 13 divided by the square root of 50, if we put that into a calculator, is this value right here, and rounding it to 3 decimal places, we get about 1.838. Let's do another example. Suppose another simple random sample of size n equals 20 is obtained from a population with a mean of 120 and a standard deviation of 13. Does the population need to be normally distributed in order for the sampling distribution of x bar to be approximately normally distributed? Well, the key here is that our sample size is 20. So looking over here at our central limit theorem, in order for our sampling distribution to be normally distributed and to allow n to be less than 30, then our population does have to be normally distributed. So therefore, we would say that the underlying population does need to be normally distributed because our sample size is less than 30. Example 3. Find the sampling distribution mean and standard deviation from the given parameters of the population and sample size. The population mean is 80, the population standard deviation is 6, and the sample size is 36. Since the sample size is larger than 30, we can assume that the sampling distribution will be approximately normal, with the sampling distribution mean being the same as the population mean, and the sampling distribution standard deviation being the population distribution divided by the square root of n, the sample size. So the mean of the sampling distribution is 80. No math to do there, we're just copying down the population mean. What about the standard deviation of the sampling distribution? Okay, so this one actually requires a little bit of math. So first we have to put in the population mean, which is 6, and then we divide by the square root of n, which is the square root of 36. So we have 6 over 6. So in this case, the standard deviation of our sampling distribution, also called the standard error of the mean, is 1. Example 4. Determine the sampling distribution mean and standard deviation from the given parameters. This time we're going to round all of our answers to 3 decimal places as needed. So our population mean is 12, our population standard deviation is 5, and our sample size is 40. So first of all, since our sample size is larger than 30, we can assume that the sampling distribution will be approximately normally distributed, with the sampling distribution mean being the same as the population distribution, and the sampling distribution standard deviation being the population distribution divided by the square root of our n sample size. So the mean of our sampling distribution is 12. No calculation needed there. We're just copying our population mean. And the standard deviation of the sampling distribution, which again is also called the standard error of the mean, is the population standard deviation, in this case that's 5, divided by the square root of n, in this case that's the square root of 40. So if we type that into a calculator, this is our answer here. And then notice we're asked to round to 3 decimal places. So this is about 0.791. Example 5. Suppose you are given the following graph of a sampling distribution. Determine the mean and standard deviation of the sampling distribution. Well, we know that the mean is always located in the middle when we have a normal distribution. So therefore, our mean must be 200. Now, how can we figure out the standard deviation? Well, remember, when we draw a normal distribution, the tick marks represent integer numbers of standard deviations. So this is the mean. The next tick mark to the right should be the mean plus 1 standard deviation. And then the tick mark to the left should be the mean minus 1 standard deviation. So since we're going from 200 to 230, can you figure out what the standard deviation should be? The standard deviation is 30. Since we're going from 200 to 230, the distance from those 2 points is 30. If the sample size is n equals 9, what is most likely true about the shape of the population? This implies that the population is normally distributed, since the sample size n equals 9 is too small for the central limit theorem to transform a non-normally distributed distribution into a normal distribution. If the sample size is n equals 9, what is the standard deviation of the population from which the sampling distribution was drawn? Well, we know that the sampling distribution standard deviation was 30, and we know that the sampling distribution is equal to the population distribution divided by the square root of n. So we have 30 is equal to the population distribution divided by the square root of n. Well, we know n is 9, so then we have 30 is equal to the population standard deviation divided by the square root of 9, which is 3. So ultimately we have 30 equals sigma over 3, population standard deviation divided by 3. To solve this, we need to multiply both sides by 3, and we find that our population standard deviation was 90. Having watched this video, you should now be able to explain the phenomenon of sampling variability, define a sampling distribution, define the standard error of the mean, and calculate the mean and standard deviation of a sampling distribution given the population mean, standard deviation, and sample size.